Good afternoon, colleagues. For those who do not know me, my name is Lloyd Sitlogo. I'm actually the Deputy Chairperson of the Load Research Chapter. Our presentation today, it's about smart metering in South Africa. So the presenter will be presenting the status and the emerging trends. The speaker, his name is Sean Papi. He's a senior advisor at Eskom Research Testing and Development based at Rocheville in Johannesburg, with over a decade of experience in smart metering systems. He chairs the SAIEE TC13 and also the APSEC TC13. He represents South Africa on IEC TC13 working groups 14 on data exchange for meter reading, tariff, and load control, and 15 also on working group 15 also, which deals with metering payment systems and contributes to the NRS 049 work group. His work focuses on advancing smart metering technologies, standards to enhance the efficiency, reliability, and interoperability of electrical systems in South Africa and the region. And I'm happy to also share with you that Sean received an award, which is called the IEC 1906 Award. So we congratulate you, Sean, again. I know you received it last month, but I think it's still proper because this is something also that made you not to be able to attend our session because you were going to receive this award. So congratulations, Sean, on that score. So really, colleagues, we can see that the person who's going to present to us knows exactly what he's talking about. I'm happy to also share with you that he is also running the testing facility at Eskom Research, and it's a very sophisticated testing facility on metering there. Maybe for 1 minute, he can also share with us what he's doing there. So without further ado, I'm going to now hand over to Sean to give us the presentation. Over to you, Sean, when you are ready. Thank you.
Thank you, Chair.
And just to let you know also, Sean, as you go through your presentation, we've got representatives here from various institutions, various sectors of energy in the country. So we've got municipalities that are represented, universities, and we've got members who have retired. We've got Eskom. So there's a number of variety of representatives here, so that at least as you go through the presentation, you can have a feel of the people who are attending this session. So thank you. You can continue. Sorry to interrupt you there.
All right. Thanks. Thanks, Chair. Afternoon again. And thank you all for affording me the opportunity. My presentation is fundamentally on smart metering. You'll see I'm very standards orientated, so a lot of that will come through. And primarily the focus or the technology that I'll be speaking about is applied in the South African environment, but mainly we've learned from international implementations, which were done way before we even started our own locally. And we've really benefited from participation in the international standardization space. And we've not only participated, but we've also directly contributed. And some of what we implement now in smart meters that are deployed in South Africa are actually contributions from our own engineers within the country. So firstly, just to give a timeline of where we're coming from, early in the 2000s, a lot of municipalities started piloting smart meters. It was mainly for the commercial and industrial sector because at the time, it was thought that the technology is very expensive and it made business sense to deploy it to customers that bring in most of the revenue. So it started around in 2000. Remember Tshwane, City Power, Eskom as well, were the first to start out on smart metering. And around in 2007, when an act came out mandating the use of smart meters in order to enable load limiting or load control at the time. Again, Eskom started another pilot, which started with around 201 with a mix of medium and large users. In this round, the residential customers were also included, but it was what we called back then the higher LSM, so around Sentin and so forth. And the focus was mainly just to prove the concept of smart metering and also load limiting. We deployed a number of appliance control devices to customers and a number of presentations on the learnings that came out from that pilot, which then informed the next round, which was between 2010 and 2016. And really in 2016, that's where we had a proper smart meter rollout with around 90 to 140,000 smart meters, particularly in Eskom. At the moment, we're sitting at around just over 800,000, which includes those meters that were deployed in 2016. And that was around the time where even the first edition of NRSO 49 that used open standards was also published. So it was quite a pioneering moment in 2016, driven mainly by revenue collection. Eskom's drive was mainly to put customers on prepaid. So the smart meters that were deployed were expected to be switchable from prepaid to postpaid and vice versa remotely. And then where we are at the moment is that 2016 introduced a cohesive approach to standardizing the technology, and then it started to mature given the amount of numbers that were deployed at the time. And at this point in time, last year, 2024, Treasury also put out a tender for smart meters, mainly to assist municipalities to collect revenue. And that also followed, in part, the Eskom standards and the NRSO 49 specification in particular. And going beyond the RT29, both Eskom and government plan to cover all customers, electricity customers with smart meters, right from commercial and industrial down to residential and even in the rural areas. And I frequent townships from time to time, and I've seen even in places where we didn't expect, there is already thousands of smart meters that are rolled out there. So the point I'm making is that it's no longer deployed only in the so-called higher LSM, but it is a technology that is now economical enough to be rolled out to every customer within Eskom and the municipalities as well. But just in terms of how the devices themselves have evolved in the past few years, we started out in the late 80s with prepayment meters, which matured over time. A very good and reliable technology, I must say, over the past few years or so. Over time, yes, it showed some weaknesses in providing the evolving customer needs, and also in terms of multiple or enhanced functionality that was needed for the modern customer. But at the time, I think when it started out, it was a revolutionary technology that worked really well. And some of the downsides of it is that if you needed additional functionality on top of the core prepayment functionality, it was then manufacturer specific. The second issue was that it was mainly one-way communication, and in that sense, it's just the online vending system communicating with the meter via a token carrier, which might be a slip that the customer buys off and goes and punches it in. So those meters would sit for a few years without any auditing or any visits from the utilities, which resulted in rising energy theft and non-technical losses. And then we moved on to smart meters, as I mentioned, around 2016. they really started to take hold of the customer base. With what we have now, we have multifunction devices covering prepayment, the time of use tariffs, bidirectional measurements as well. And I think a key feature is that we are using a common data model to model the functionality. I'll speak more about that later on. And also reliance on standard communication interfaces. Previously, every smart meter vendor, and now this is prior to 2016, would provide their own proprietary communication interfaces that would match their backend system. So basically, if you procured a smart meter at that time, you'd have to buy the IT system as well to manage that. And if anything goes wrong, it means you had to decommission not only the smart meters, but the IT systems as well, because they were built to work with each other. So in 2016, another pioneering feature was that the communication interfaces were based on standards, meaning that multiple vendors could implement the same technology and be able to take advantage of existing IT infrastructure. And then, of course, that introduced two-way communication. And also, you could see the difference between the two customer interfaces. The current one is much richer in data and provides the customer with much more information than just the available credit, which was a feature of the older CIUs. And then moving forward, I've stated here near future because it's not too far off, probably a year or two from now. We would then see the introduction of modular communication interfaces. This might have been prevalent in the meters using cellular communication, but we were not able before to exchange power line communication technologies while retaining the physical meter. So we are seeing a trend where meter manufacturers are bringing into the market meters that enable the exchange of even power line communication modules. So it would be good to adopt that in order to ensure that the installations are future proof and that also we are able to take advantage of emerging communication technologies that, of course, will be faster and more secure in future. And also the customer interface unit introduces a lot of maintenance from Eskom side or the utility side. Also, it becomes a source of many calls from customers because the customers handle it and and it's in their premises as well. So going forward, the customer interface unit will eventually be obsolete and be replaced with customer-owned devices, so smartphones, etc. The idea is that at least if we could use, if we could then provide the same rich customer information on their own device. By default, that device is maintained by the customer. The customer already takes care of it. All that the utility needs to do is ensure that the customer has access to their data and also would then integrate features like virtual tokens, which are already available, but we do not have the IT infrastructure at the at this point in time to enable the delivery of STS tokens over here. But as I say, in a year or two, this should be a possibility. The technology is available. I think what is lagging behind is adoption and wide-scale implementation. And I really like to give a clear definition of what we understand a smart meter to be. The term smart tends to really confuse the discussion at times. So when we say smart, we have a lot of smart things nowadays, and the expectations might be far higher than what the technology actually provides. So I've provided just hopefully a simple and but comprehensive at the same time definition. Essentially, the smart meter is still an electricity meter. The difference is that it has multiple functions, can handle multiple tariffs and energy measurements. It has control functions and, of course, secure two-way communication. And for the rest of this presentation, I will deal with each of these features. So in terms of multifunctionality, within the smart metering standardization space, functionality is defined as through use cases, and then it is modeled or built using data models. I'll share more on that as we go forward. And the fact that it's still a meter, it still needs to measure energy. So the issue of metrology becomes important. Secondly, no matter how smart the meter is, if it's not compatible with the environment that it exists in, it will quickly malfunction and it will be all the smart features will be in vain because that meter would not be functioning correctly. And then, of course, safety is always important, both for the customer and also for the utility. And also two-way communication, and not only that, but the communication must also be secure, especially in the time that we live in, where the IT technologies have advanced so much that it provides tools for even those who are criminals have access to those tools. And therefore, we need to ensure that the customer data is secure, that the installation base is secure, that we don't suffer from hacker attacks that cause outrages and cost us money and reputation as well. So I'll look at those three concepts in the next few slides. Right. Firstly, I just wanted to deal with metrology, the environmental compatibility and safety, and that is addressed in the IEC standards, I think, which are well established at this point. What is new is DC metrology, which we didn't have previously. But in the past 2 years, the standard for DC metrology was published, and that then offers us an opportunity to do DC measurements, for example, on EV charger installations. If we want to build them on DC, we can then demand that they use the standardized DC meters that have been standardized according to the IEC standard. That possibility is available. And I know in Rwanda, a few years back, I was exposed to DC appliances where the customers would supply the appliances directly using DC. And this provides an opportunity for utilities to be able to ensure that the energy consumed is measured accurately and catered for. And of course, energy control, so remote disconnect, remote reconnect. We also need to ensure that it is safe. It lasts the time that the supply control switches in the meters last the time that the lifetime of the meter, that they do not fail before the meter reaches the return on investment period. So generally, the standards cover the standardization of electrical values. Example, in the US, they would use 60 hertz. We use 50 hertz. And so our measurements are based on a frequency of 50 hertz for the AC measurements. So that needs to be standardized as well. Construction requirements, accuracy requirements, I've already alluded to that, that whether the meter is smart or not, it still needs to be accurate. Climate, we know our own climate variations in South Africa itself. Cape Town, it's a bit dry. Durban might be a bit wet in the air and warm. You go to Limpopo, it's dry and hot. The meters need to operate correctly and communicate correctly in all those climatic conditions. So the standards provide us, for example, a temperature range in which those meters must be able to operate. And again, the influence of Africa came in before. The temperature range was very narrow. But in the 2020 edition that was published, The temperature range was made a bit wider because Africa tends to be much hotter. And then there's issues around EMC, resistance to lightning, to electrostatic discharge, and to switching transients as well. And then in terms of safety, the protection against electrical shock is covered as well, where the meters are tested to see how well their enclosure, so their design prevents electrical shock and so forth. The issue around supply control switches as well. How much current can those switches disconnect safely? How much current can they reconnect safely without compromising the safety of the customer and of the utility installation as well? And you'll see the AC meters cover both active and reactive, so that the meters that we specify cover bi-directional energy as well. So we cover both export and import energies in a single meter, unlike the previous technologies that only provided for import energy. Okay. I just then wanted to provide a reference architecture for smart metering. And this comes directly from the IEC standardization framework for smart meters as well. You'll see I've got three colored squares. They are separating the scopes of the different technical committees. On the right-hand side, TC13 is the one that covers the core smart metering functions. But you'll see that at IT level, it then also interacts with Technical Committee 57, which is responsible for system level management of power utilities and also the data that's exchanged to facilitate those management functions. And then you'll see on the left-hand side, there's an interaction again with the SC23K, which covers products for energy efficiency. So essentially, the green block covers the home energy management systems and shows that the standards have already catered for communication interfaces with those devices in a standardized way using a standard data model, so that the data coming from the home energy management systems is interpretable within the smart metering domain and also within the systems domain. Essentially, this is what the picture is showing to us. And of course, going forward, we'll just focus on the orange picture because that's where the smart metering technology is mainly standardized. The green block represents the customer interface. This is not some interface unit. This is not something that is used in the US or in Europe. Mainly, they would use home energy management systems or displays that are owned by the customer. But in our domain, right from 2016 up until now, we have provided meters that go together with the customer interface unit. So this is, again, a contribution that we've made to the standardization arena, which is a very South African specific requirement. And also now it's expanding into the continent as well. All right. So we've covered the metrology part, and I've given you the overview of the architecture of how, in general, smart metering systems are organized. So in terms of communication, again, here we rely very strongly on standards. And in particular, we rely on a standard series called IC 62056. Many or some of you might know it as the DLMS COSEM standard, if you've come across that. But essentially, it is composed of a number of components. The first three in gray at the top. So those represent the services, which is in 6056-5-3. Services essentially the messages or how the data model must be packaged in order to be transported inside a communication media, like a cellular network or a power line communication network, and so forth. So the services define how that protocol unit must look. in order for it to be carried in those communication media. And just above it, there's two important standards that give us the data model. And I'll explain again going forward what that entails. But in short, the data model defines how the data must be, how a function must be modeled, and what data elements must be included in that function, and then how those data elements should be interpreted by all entities within the smart metering system. So that's the role of those two standards, the OBIS code standard and also the COSM interface classes standard. And then just below it, you'll see, I'm not going to go through everything, but what the blue and the orange blocks represent are standards that tell us how we then carry the data that is encapsulated according to the services standard inside specific technologies. So you'll see HDLC, for example, here you see Prime PLC. And so for each and every communication media, there would then be a standard that defines how the services of DLMS COSM are used over that communication media. That is generally the idea. So you'll see every time there's a new use case, there's a new function, the data model will expand, but the services remain fairly consistent over the years. And then also every time there's a new communication media, we had 3G at some point, then we had 4G, now we have 5G, and we are moving over to 6G. So in order to ensure that we don't have to reinvest in the IT infrastructure every time a new communication media comes along or a new use case comes along, the application layer services remain consistent so that the new communication media is integrated the same way, and the new data models is also implemented according to common rules. So this protects the investment over time and ensures that we take advantage of use cases that we have not defined now, and we also take advantage of emerging communication technologies. As we know, the communication space is more innovative than any other space, and they keep coming up with new technologies to improve the communication and to make it more reliable. So we should not be then in a position to always be reinvesting in the base infrastructure that we have. But if we apply these standards, we'll be able to take advantage of both use cases and emerging communication technologies without really breaking the bank in terms of IT infrastructure. And then the second part that's covered in those standards, which is not shown in the previous image, is security. And the standards basically take proven security mechanisms that have been standardized through entities such as NIST in the US. And you'll see for now, there's 3 security suites that cover authentication, that cover encryption. There's also digital signatures that can be used. And these mechanisms can be applied in a layered approach. For example, you could have just authentication and encryption as the initial security feature. And then over time, if you see that you need more advanced authentication or entity authentication, then you can move to digital signatures. You could also move from security zero to security one and increase the encryption, the size of the encryption keys, and strengthen your security over time. And of course, the higher the longer the encryption keys, the more processing power you'd need in the meters themselves. So from the onset, when you specify the metering infrastructure, one should keep in mind that going forward in future, we might need to strengthen our security mechanisms, and therefore we'll also need to specify to those who are delivering those meters that we would need to also have sufficient processing power going forward if we need to update our cybersecurity on the meters. So this is clearly defined in the standards. And what I like, as I said, is that it's layered. You can select the type of security that you want, and that would still also be implementable with the application layer services that I showed in the previous slide. Okay, so let's get into the use cases and the object model. Over the years, I think the standardization work started around the late 90s. And of course, there were hundreds and hundreds of various use cases that were explored. I know in Europe, the EU funded a project around 2009 to do an exercise of defining standard use cases across the board. So the list that you see is a list that has been captured over the years, taking input from different countries all over the globe, and we've reached sort of a set of standard use cases. And of course, as I said, the idea is that you standardize your infrastructure in such a way that if a new use case comes along, you are still able to take advantage of it or implement it. But at the moment, this is what, as we speak now, is implemented in the current meter technology that follows the IEC standards at this point in time. And you'll see very familiar use cases like remote disconnect, reconnect, load control. Clock synchronization has been there for some time. Consumer information important for our environment, given we deploy customer interface units. Recently, communication supervision has become important, so the meter is able to report if there's a degradation in the performance of the communication media it's using. A new use case is use case 13, UC13, which, as opposed to firmware updates, because what we do now is that if we introduce new features, we wipe the old firmware from the meters and then we upload a new firmware. And again, it allows us to reuse the hardware, but still be able to cater for new and future features. So, but it tends to take long, and it's also, let me say, risky. If you don't do it properly, you might break something there. But UC13 then says you can change a subset of a function instead of changing the entire firmware. So that came out recently around 2022, and I think it's a great feature because then you could just switch off remote disconnect, for example, and then switch it on whenever you need it. And then we also contributed to the IC, the payment metering use case from the South African side to accommodate prepayment functionality as well. Okay, and then in terms of object modeling, you'll see I've got a meter display. So this is from a CIU somewhere in Eskom. You'll see that it displays the energy consumed to date. So that would be 13170 kilowatt hours. And at the bottom where you see the red arrow going, that table is called an interface class. So if you recall, a few slides back, I did mention that there is a standard that defines a number of interface classes. So a register is something that we in the metering domain have had for time eternal. So it has now been modeled as a class that has a value and a scalar and a unit. So the scalar would be something 10 to the minus 3, 10 to the 3, to the power 3 to represent kilo, for example. And then the standard defines standard units such as watt hour, var hour, VA hour, and so forth. And those are updated as new units emerge or as there is a need to introduce new units. So you'll have this class that will then be used to define the register functionality in the meter. So you might have a kilowatt hour register, you might have a kilowatt hour register, you might have a watt register, for example. And those registers will be built from this same table but they would have a unique identifier so that they are objects instead of classes. In the next slide, I'll show you how those are implemented. So what I was demonstrating here is how we then marry what is implemented physically on the display that is acquired from a software implementation of this register class. Then on the left, same idea as the previous slide. You first define the use cases and then you select the classes that model that functionality. And the combination of those classes is called the object module of that meter. So if I take a meter from Eskom now and I read all the objects in it, I should be able to have an idea of the type of functionality that it supports, even before reading a manual or something to that effect. And then the application layer services, I've explained earlier, it's just the formatting or the structure of the messages that carry the objects or the attributes of the objects over the transport, which can be LTE, it can be YSAN, it can be G3PLC, and whatever else that is coming in future. Okay, so this table is one of the tables that comes from the IEC standards that defines interface classes. I've put it here just to give you an idea of a subset. For example, on the payment metering, which is on the right-hand side, you'll see that there's a class defined for the account, a credit, a token gateway, and the STS attribute. So you would be able to then model a customer prepayment account in the meter that will manage the credit that the customer inserts, and as the credit is consumed due to variations in customer load, then that would be also registered in the account. So you'd be able to have a record in the meter of the transactions and the interactions between the credit account and the charges that you've defined in the meter. And on the right-hand side, you'll see there's register activation. There's hundreds of these interface classes that are used in the meter. But how this helps in ensuring that the IT systems that we put in place understand the structure of the data that's coming to it, and they can also understand the meaning that comes to it in a consistent way. So a meter that is used in Eskom can then also be used successfully using IT infrastructure that resides in another municipality without the municipality having to reinvest or change their IT system. That is really the idea of painstakingly breaking down the functionality into classes and then putting them together as objects inside the meter firmware. But that saves us a lot of time in the deployment stage and also in the definition of specifications. Okay, this picture just gives an overview of a meter and how certain objects will then interact with the meter application process or the central firmware core. So you'll see there's a clock, which is also an object that is defined as a class in the standard. There's disconnect control, which facilitates remote disconnect, load limiting, and those type of functionalities. That also is modeled as a class. There's token credit and so forth. And all these components are deterministic because their behavior is defined in the classes that they have. So for utility engineers, then it becomes easier to specify functionality, and then secondly, to evaluate that functionality, and lastly, to integrate those smart meters into existing or new IT systems as well. And you'll see on the left-hand side, there's a LAN interface and a WAN interface, and the meters uh, do have a number of interfaces for local communication, for remote communication. But if you connect through those interfaces, the information that resides inside the meter is exactly the same through each interface. And then the manufacturers are also allowed, following the rules of the standard, to define their own manufacturer-specific objects, perhaps maybe to differentiate their product from the others or to introduce a more advanced feature. That is allowed as long as it's structured and modeled according to the rules of the standard. Okay, and then in the last few slides, just wanted to zoom in into a few capabilities that the current smart meters have. In terms of load profiling, you can go down into a 1 minute interval. I know generally in South Africa, we measure consumption at 30-minute intervals. But however, if you really want granular data to do whatever studies that you'd like to do at that granularity, you can go down even to 1 minute and up to 60 minutes. That's how flexible the data model of the current meters are. And then in terms of spatial granularity, as I said, the meters have communication capabilities in them. For example, for a set of meters using a cellular network, one might be able to identify the location of those meters remotely using their GPS coordinates that is indicated by the GSM modems that reside in those meters, and be able to then group those meters into a residential area, a particular feeder, and so forth, so that you are able to marry the data to a particular spatial entity or geographical area. We've mentioned this before as well, that off the shelf, the meters are multi-energy, so they cover all types of energies. And recently, they also do power quality reporting, but not to replace power quality meters, specialized power quality meters, because the standards demand more from specialized power quality meters. However, the smart meters provide a toned down power quality reporting. So, for example, you can be able to monitor variations in mains voltage and report on that. You can monitor the frequency of the system and set boundaries so that the meter can report events and alarms where there is a shift away from the required frequency boundaries, for example. You can look at power factor. You can look at the last time the meter switched off, the last time the meter powered on, and these can be recorded as events. If you do look at the current standards now, you'll see the amount of events that are already specified in the cover a lot of the occurrences on our networks, and that would assist greatly to detect problems in time. And the other advantage is that because we have this rich data set, there is no limit of the type of applications that you can build on top of the smart metering system. Okay, and then in terms of load control, we are then able to control the meters individually to reconnect, disconnect customers, for example, or as a group, can set a group command to switch off Sentin and not the rest of Gauteng or not the rest of the area, just Sentin alone or a group of customers within Sentin that you want to disconnect. There's a concept of load limiting that has also been widely implemented within Eskom the last few years. What it entails essentially is that instead of cutting off the customer or load shedding the customer, you simply just then lower the total amount of current that the customer can pull from the network. So you can move from 60 amp to 10 amps, meaning that the customer still has a capacity of 10 amps to use to watch TV, to keep the alarm on, and so forth, be when the system is constrained. So that is a feature that is currently already available and implementable in the meters. We could also use the load profiles we discussed in the previous slide to see typically how much that customer uses per day. You'll find that they don't even reach the capacity that they are contracted for. So even load limiting them might not affect them that much. So one can look at the data and say, okay, this customer sits around 40 amps most of the time. So we can shave off that when we have system constraints, we can shave off 20 amps and they will still be able to operate normally. And if they exceed the 40 amps, it's only then they will then see the impact of load limiting on their house. And again, you could prioritize, select, or just disconnect a few loads within the customer base, depending on what you need. For example, if you've got a very large customer that you can disconnect on its own and then leave the rest of the customers and still be able to protect the system, that is a possibility. And of course, remote disconnect, reconnect, that's a well-tested feature at this point in time that allows us to reduce the time and the money to go to a customer and disconnect, or even when we need to reconnect, then we can do it remotely. Okay. And then I think for me, the one important feature is the ability to have multiple tariffs or to program different tariffs as you need on the same meter. When I started in metering, you had a special meter for a particular customer segment. So for the prepayment users, you had a meter for them. For the small power users, you had a meter for them. For large power users, you had a different meter. But because, again, the tariff needs were different. But smart meters give us the flexibility that on the same meter, you can service different customers and you can also introduce different tariffs as and when required. In the UK, for example, they have a 48 time interval, time of use tariff, meaning that they can split a day into 48 intervals and have prices for each interval. So every half a minute or half an hour, I would imagine that they would then have a different price, for example. That is a possibility that is already implementable. They've also implemented a combination of time of use with block tariffs. So in each block, you also have time-based prices within that particular block. I haven't seen the tariffs themselves, but I've seen meters that are capable of doing that. And also, we are now also able to implement prepayment time of use tariffs. So before, the prepayment would be on a block tariff or a flat tariff, but with the current smart meters, you are able then to implement a time of use tariff that is paid by the prepaid account as the customer consumes that energy. You also have the possibility to then credit the customer on the meter itself, on the meter account, so that when the meter measures the export energy coming from the customer, where, of course, this is authorized, then that export energy that is registered by the meter can then be used to credit the customer's prepayment account that resides in the meter. These are possibilities that are available, of course, subject to regulation and tariff approvals by the likes of NESA. Okay, so you can do also critical peak pricing or event-based tariffs. That is possible. The other important thing is that every smart meter would now is capable of measuring both export and import energy, and then can then support net metering as well. And then I've touched on power quality. What I just wanted to emphasize here is that you can then define the type of events that you want to monitor. The meter keeps a power quality log and a power quality event log, and those are also programmable as you require it as the utility or the power quality engineer within that utility, so that we can be able to capture the events of your interest. And also, these are based on the COSEM standard model as well, meaning that they are modeled in a common way that is understandable by different systems. And why that is important, you'll find that the revenue protection engineers within a utility might use a certain system and monitor different set of objects. And then you'll find that the power quality engineers also use a different system and monitor these objects that relate to power quality reporting. So that enables that flexibility within the system as well. All right. Thank you, Chair. That was my last slide.
Thank you very much, Sean, for the very interesting, exciteful, and informative presentation, telling us where we are in terms of smart metering in South Africa, and also giving us the history of where we come from, which is really great to note that we have really moved forward, we have advanced, and I believe there is now the rollout process which is underway in the country, and I believe we'll be able to benefit more from the smart meters. Already you have shown some of the use cases that one can be able to use. Colleagues, before I have one or two questions or even comments on my side. Is there any question for Sean from the audience? Now is the time to ask him that question. You might not have that opportunity. Karen, I see you have unmuted yourself. Do you want to say something?
Yes, please. Thank you. Sean, I really enjoyed the presentation. It's interesting to see where we are and how things have developed and what the capabilities of our meters are at this stage already. I noticed you mentioned that you also use it for load limiting, and I was interested to hear that, because that was going to be one of my questions. And I just wanted to know whether you have, in fact, applied it quite a lot, and what people actually do if they then want to use more and they switch on more than what the meter actually allows in a load limiting situation. Just a quick question. Thank you.
Thanks. Karen, in the South African environment, I must say it was well received. It was implemented in the Sentin Midrand area. I think a colleague of mine does have a report on that. But nevertheless, it has now been rolled out to other operating units within Eskom. In that pilot in the Sentin Midrand area, it was well received because of the reality of load shedding. So the customers, especially the residential customers, preferred to at least have some power instead of being cut off entirely. So during load shedding for 4 hours, at least they'll still be able to watch their favorite soapy. So that was a plus, and keep the Wi-Fi on. And I must say, we didn't have a lot of complaints in terms of exceeding the limit, because I think, fortunately, it was implemented during load shedding. So a lot of customers were aware that they had minimal energy available to them during those periods. I think the only issues were when load shedding had completed, uh, perhaps you have a cell phone tower that had gone down and took longer to come back online, and that means the message sent from the head-end system down to the meter to revert back to the normal current limit did not reach the customer in time. So it was those type of issues, but generally it was well received. Yeah.
Thank you. That's a very good, gives a very good overview of what happens. But now, if they do then like switch on the kettle and it exceeds the limit, does the meter then just simply switch them off and then reset after a while, or what
Oh,
happens?
yes. Okay. Yeah, it would then just cut them off for a minute. And then, of course, it has to check. So it has to reconnect. It will reconnect again. If the customer still exceeds, it will do this 5 times. On the fifth time, it will lock out, meaning that it will disconnect the customer entirely. So if it did, the customer exceeded and it did disconnect the first time, normally people would then be aware that I've done something, and then maybe lower their consumption, and then they know they'll be on for longer. But if not, you'll be cut off for 30 minutes after the 5 retries.
Thank you very much. That gives
Yeah.
a very good overview of what's happening, and especially for most of us, we weren't aware what it entailed. So thank you very much, and it sounds like an excellent way of reducing load without cutting people off completely. Thank you.
Thanks.
Thank you, Karen. Is there any other questions, colleagues? Whilst we're thinking about that, one comment from my side. The first one is that because we are in load research here, I think we'll benefit more in terms of our sample size. This will increase really our sample size because for many years we've been battling, especially on the side of Eskom, where we have installed a few data loggers just to be able to access the load profiles from the residential customers. So the rollout of these smart meters will indeed assist us a lot by increasing our sample design. So we really appreciate, and we cannot wait actually for the rollout of these smart meters. The second point that I would like to make, which is more of a question, you mentioned something about the aggregation. I think it's one of the capabilities of the smart meter that we are able to aggregate the customers per feeder, as an example. What's the difference between this aggregation per feeder with the data concentrators that are sitting there on that particular feed?
Oh no.
Or
So if remember, there's a number of different communication technologies. So I used aggregation as a general term.
okay.
So one would have meters that use cellular communication, for example, where there's no data concentrator at feeder level. So there you'll just need to use the, hopefully it's correct, the data on the network where the meters sit within that feeder. And then you will then create a group on the smart metering hidden system to say this group of meters. I will then aggregate their data because they sit under feeder 1, 2, 3, 4. And then on the data concentrator side, at least there you'll be aware that that particular data concentrator sits under a particular substation, and then you can then interrogate it for the meters that are connected to it on that particular network. Yeah.
Okay.
And again, if you wanna look at it per feeder, normally the data concentrator would monitor 3 feeders. And then within the DC itself, you are able to differentiate figure A, B, and C. And then if you choose to monitor only one, you know that those meters sit there. On the cellular network, you'll have to rely mainly on the installation and commissioning data and the GIS data in order to identify which meters are sitting on that particular feeder. Once you've done that, you can then create a group on your monitoring system to collect the aggregated data.
Okay. Thank you very much, Sean, for responding to that. Is there any other question or comment before we release Sean? I don't see any hands. It means, Sean, your presentation was well received and well understood. Again, we want to thank you for the time that you have made for us to come and present to the Load Research Chapter. Sean, on behalf of the Load Research Chapter and the Executive Committee of Load Research Chapter, we thank you so much for spending time with us. So I have seen the applause from the colleagues here. So we really appreciate their time. Thank you, Sean. You are excused if you maybe want to attend other commitments.